All right, good morning. If you'd like to get out your trend note sheet as well, we're going to be kind of referring to that a little bit, but we're going to kind of elaborate on some main topics today.
Hey, Mr. Gussie, where do you get all your music? Do you just go on Pandora? I don't know if you customize your playlist or not. I didn't know if you were that kind of person.
You hit the thumbs up or the thumbs down, right?
Well, no, you can on Spotify, you can pick out your song and put them on a playlist and be yeah, I'm gonna rock this here. Do you pay for your Spotify account?
I just do Pandora. Okay, so you can elaborate as much as you want on some things. You're going to be getting into some groups in a little bit, and you're going to elaborate on some of these questions. These are very realistic AP questions that could and probably will somehow show up on your test on Friday. Just as a reminder, you have atomic structure 2 due today. There's an optional review after school today. Your spectroscopy lab is due by tomorrow. We have a test on Friday, and that is when your bookwork and lesson 10 packet is due. Please don't forget about the problems at the end. Please don't forget about the problems at the end. That will hurt you a lot. Those problems are worth double any exercise problem. So I always make problems worth more because it's you got to structure it yourself. So if you were curious about your unknowns, you may have it in front of you or not. It's okay. But these were the unknowns to the lab. So I don't know if you even can recall how close you were or not. But the first unknown was 0.3244. And the second unknown, drum roll please, 0.17965, very precise. So, just curious how close you are, and hopefully you were pretty close, I'm not sure. But those are the unknowns. Thank you. Did you get a sheet? Okay. All right, so today we're going to focus on 2 trends that really affect everything, and we probably have elaborated on them already, but you can write as much or as little as you want, and then we're going to elaborate a little bit more on this sheet as we go. So, but first, I forgot about this. Sorry.
Put on your glasses.
Thought this was later.
You might want to grab a pair of binoculars too, or a magnifying lens.
Wow, that came out of nowhere. This is really cool. So we're talking about electrons and we're talking about energy. Can I ever get this off? There we go. So maybe you've wondered this before. This links directly to what we're doing right now. This is pretty cool. So sit back, enjoy, and hopefully you feel like you really learned something from just this.
Take a look out your window. Put on your glasses if you wear them. You might want to grab a pair of binoculars too, or a magnifying lens. Now, what do you see? Well, whatever it is, it's not the multiple layers of glass right in front of you. But have you ever wondered how something so solid can be so invisible? To understand that, we have to understand what glass actually is, and where it comes from. It all begins in the Earth's crust, where the 2 most common elements are silicon and oxygen. These react together to form silicon dioxide, whose molecules arrange themselves into a regular crystalline form known as quartz. Quartz is commonly found in sand, where it often makes up most of the grains, and is the main ingredient in most types of glass. Of course, you probably noticed that glass isn't made of multiple tiny bits of quartz, and for good reason. For one thing, the edges of the rigidly formed grains and smaller defects within the crystal structure reflect and disperse light that hits them. But when the quartz is heated high enough, the extra energy makes the molecules vibrate until they break the bonds holding them together and become a flowing liquid, the same way that ice melts into water. Unlike water, though, liquid silicon dioxide does not reform into a crystal solid when it cools. Instead, as the molecules lose energy, they are less and less able to move into an ordered position. and the result is what is called an amorphous solid. A solid material with the chaotic structure of a liquid, which allows the molecules to freely fill in any gaps. This makes the surface of glass uniform on a microscopic level, allowing light to strike it without being scattered in different directions. But this still doesn't explain why light is able to pass through glass rather than being absorbed as with most solids.
This links to the chapter right here.
We need to go all the way down to the subatomic level. You may know that an atom consists of a nucleus with electrons orbiting around it, but you may be surprised to know that it's mostly empty space. In fact, if an atom were the size of a sports stadium, the nucleus would be like a single pea in the center, while the electrons would be like grains of sand in the outer seats. That should leave plenty of space for light to pass through without hitting any of these particles. So the real question is not why is glass transparent, but why aren't all materials transparent? The answer has to do with the different energy levels that electrons in an atom can have. Think of these as different rows of seats in the stadium stands. An electron is initially assigned to sit in a certain row, but it could jump to a better row, if it only had the energy. As luck would have it, absorbing one of those light photons passing through the atom can provide just the energy the electron needs. But there's a catch. The energy from the photon has to be the right amount to get an electron to the next row. Otherwise, it will just let the photon pass by. And it just so happens that in glass, the rows are so far apart that a photon of visible light can't provide enough energy for an electron to jump between them. Photons from ultraviolet light, on the other hand, give just the right amount of energy and are absorbed, which is why you can't get a suntan through glass. This amazing property of being both solid and transparent has given glass many uses throughout the centuries, from windows that let in light while keeping out the elements, to lenses that allow us to see both the vast worlds beyond our planet and the tiny ones right around us. It is hard to imagine modern civilization without glass. And yet, for such an important material, we rarely think about glass and its impact. It is precisely because the most important and useful quality of glass is being featureless and invisible that we often forget it's even there.
So, pretty cool. If you've ever wondered that before, I think they propose that really well. Like, the question's not that why is glass transparent, it's why isn't everything else? It's because when photons and energy comes in to an object, it causes the electrons to jump and it can get to the next level. But with glass, the energy levels are too far apart. I think they were off on one little thing. They were just like they could get a better seat. Well, better seats aren't further away, so but you get the idea. So with glass, the electron will jump and it won't find the next area where it could be, the next energy level, so it'll fall right back, so it can't absorb that energy or that photon of light, and the light just passes right on through. We will be talking more about this later, but I feel like we hit this in the beginning. This is the electromagnetic spectrum. What do you need? You need to know from this. You need to have some general basic ideas for Friday and throughout the whole year. So this is actually a really good image because it shows the wavelengths. Okay, you got gamma on the left, and gamma could be on the right. Can't get so stuck in one photo that you can't translate this if it gets all flipped. A lot of images online are the exact opposite images. But wherever gamma is, we're going to have shorter wavelengths. That means the energy increases. As you move across, you have longer and longer wavelengths, okay? And this one's based on nanometers, so that's why it might be a little confusing on this side for you if that doesn't seem to recognize what you've been accustomed to. And then we have Roy G. Biv, but it's Viv G. Rohr. So what we're going to need from this, we're going to practice this a little bit more tomorrow, are these equations. And that one's on your sheet. I believe that one is. The constants are on your equation sheet. And then we have Dubrow-Glaze equation, which deals with mass and velocity. So we can figure out a wavelength because there's a dual nature to light, where it acts like a particle and like a wave. So it will have a mass and it will have a speed. And then we could be talking about the amount of energy it takes to remove an electron, or for an electron to absorb or to release energy. And it'll only be this Z is always atomic number. That will be always 1 because it's only on hydrogen, but they always give a generic one. So basically what you don't have to have this number memorized, but we would have this value, and more or less you are dividing it over the energy levels squared. and that would give us an amount of energy. But that's not a huge equation that would come up, that would have one problem on a test. That would be about all that would be required of you. So this all kind of relates. Lastly, in normal electromagnetic spectrums, if I ever ask what type of wave, and we'll look and apply this tonight and tomorrow, if you come to the review and tomorrow during class, if I ever ask like what type of wave, it is almost always asking you what type of wavelength then. Like what type of radiation? Well, you probably need to find lambda somehow. Okay, so that being said, a couple things, and you probably already have this written down if you want to make extra notes or not. We are going to elaborate very well on very specific situations. So I want to hit the two main topics that matter the most to you. And again, you probably already have this somewhere, so it's more about just make sure you file this away because in about 5 minutes we're going to be applying it. Atomic radius. It's all about the radius. It's all about the distance from the last electron to the nucleus. That's what matters. So when I look at this, I can see a trend. So when I'm going across, you need to be very clear. The nuclear charge is increasing. And I believe we wrote that somewhere, but again, I'm giving you the main huge points. When I'm moving down the periodic table, we have to make sure that we're focusing on increasing energy levels and shielding effect. Okay? Those will be the basis of all of our arguments. Whenever you're asked about the size of an atom, those will probably be at the root of your explanation. So you need to know when it matters and when to bring those up. You cannot talk about nuclear charge moving down the table because you're gaining nuclear charge. The nuclear charge is gaining a stronger positive center, which would cause an electron cloud to be sucked in towards it and be held tighter. We're getting larger. That's a contradiction. You can't do that. So you have to be really careful on what you're discussing and when you're discussing it. All right? So it's all based on the atomic radius, though. So if you are asked about any of the other ones, you can still go back to the distance or the strength of the hold of my nucleus to my outer electron. Okay? The other one, the only two I want to talk about today, because it's the two that come up the most, ionization energy. Energy to remove an electron. So it's about the difficulty or the ease in removing that electron. So again, let's talk about both ways. It decreases down, so it gets less and less, and it's not about you memorizing numbers. If you're ever given values of ionization energies, you just say, thank you very much. I can see that's stronger or weaker. The larger the value, though, the more difficult it is to remove. So these numbers are getting smaller. It is important to understand that. It's actually called ionization energy. It's the amount of energy needed to remove. So it decreases down due to the distance of the valence electrons to the nucleus. You could also say the weakened attractive pull or force of my nucleus to my electrons. Okay? So that still relates back to size, right? It's the distance. So I'm getting larger. The electrons are getting further away, so that attractive force is getting weaker. And this does not hurt to review these two because, yeah?
Is there like a word that is there like a word that opposites it? Like, I can't think of like how easy it will.
As you move down, it becomes easier to remove an electron. Yep. So it would require less energy to remove it. As I move across, you can see, where are the transition metals? Transition metals screw a lot of things up, so a lot of tables don't show that. Transition metals are very valid and important, but in general, these are easier to discuss as a collective whole. As we move across, it increases due to the increased nuclear charge. You're not gaining energy levels. The electrons aren't getting further away. So what's the only big difference then from one to the next? Is I'm gaining nuclear charge, so I'm gaining a stronger nuclear pull, which causes the electrons to be held tighter. If they're held tighter, it's more difficult to remove. Talked about that last week. If I'm holding an object like a football close to my body versus far away, it's going to be much more difficult to remove it. So the electrons are closer. It's going to be more difficult. More difficult means more energy. You guys should be able to relate. You're in your teenage years. Sometimes it's just like you got to, oh God. You're not going to get my pie for me. I have to walk all the way to the kitchen and cut it even. I have to cut the pie, forget it. And then you just start eating the pie right out of the dish. You're like, thank you. Low energy. You're like, oh my gosh, that was last night. How do you know? Mom, Dad, we need security. All right, so that being said, what I'm about to do, we're going to do a little different things here today. You are going to get a chance on your sheet to write, let me see this. We're going to do all this, but I'm going to separate and give only one group, so we're only going to spend about 5 minutes. Certain groups are going to work on different topics, so they really focus on it. I might call on certain ones to present. Okay, so someone might have to stand up and actually present, and you can read literally what you wrote. Okay, but I kind of want a change of pace here for a large group. So this is what we're going to do. You can, Rory, yes.
What does FRQ stand for?
Free response question.
Oh, okay.
Okay.
Is that like a no-brainer? Like,
No,
oh, okay.
we don't want to talk about it in this class. A lot of other classes have FRQs, but we usually don't talk about it like that.
Okay.
Okay. So I have big whiteboards over here. I have, it can be one per group. I hope I grabbed enough. Oh boy. I think I did. Markers and then a paper towel if you need to erase, because you're going to be doing some different ones. And sometimes I might call for people, sometimes I won't. So here we go. These are your groups. So you can move wherever you like. You can stand, like people can be in the front, people can be in the back. All right, this is where we're going to end class, so you can bring your stuff to that area. Let's do it this way. Wherever this is where you are. So this group is up here. This next group's here. Next group's there. Next group's there, okay? Let's try to make it so, like this is the front middle, second middle, third, fourth. So this group's meeting down here. Next group, next group, next group. Bring your stuff. Please move to where the actual box is. So again, like Kyler, Matt, and Carissa, you're the second group over here somewhere. Someone needs to grab a board. Someone please grab a board and a marker. Who's not here today? Because I can switch some groups. I might have to move a few of you. Wait, Drew's not here? Who else? Annika? No, Layla's here. Emily's not here. I took her out already. Austin's here now. Nick, you're moving to this group.
I don't know.
Luke, Christian, you can handle it. Nick, I moved you. Just no. Okay, Nick, I moved you. You're the middle top now. Middle top. Let's not make this complicated again. This group's in the middle. This one's in the middle, second, third, fourth. You guys can be the power two, okay? All right. Have you? That's true. I do remember that now. All right. Wow, that transition, that was difficult. Do we all have a board? I think so, right?
Yeah, I grabbed an extra.
That's right. Now, you can also be writing on a sheet eventually. We're going to practice first as a group to discuss some things. So, sorry. All right, we all good? In the beginning, what we're going to do is we don't need the boards yet. We're going to use them in a minute. If you want to write on the board to talk about it in your group, that's great. We're going to discuss some differences with some atoms, some different elements and their ionization energies, okay? So if you want to write on the board, that's great. We're going to eventually write them on there, so you may feel like, well, I don't want to write on there right away because I don't know if I'm right or not. And so on and so forth. That's fine. Some of these situations we've already run into, and I quickly did it. I know there was one class that, like, the bell was about to go off, and I'm like scurrying to try to write it as much as I can. So in general, you don't necessarily have to write this down, but just understand, but it's your notes. You can do as much or as little as you like. When you look at a grid like this, your responsibility, and you'll start to see with every question that I give you, it's not necessarily your job to know, although you should, that one is stronger than the other, one is a larger value than the other. It's more about your job to be able to explain the situation that they give you. Like they say, hey, A has a greater ionization energy than B. Explain why, or account for the reason. Okay, now it's on. They told me something. I need to now justify it. So that should give some ease to your approach. You shouldn't feel like, oh my gosh, I don't know exactly the values, or what do I have to memorize? You have to know the trends and the reasons in general, okay? So these are all indicating that these are more difficult to remove an electron as we move up, and these are all easier to remove, okay? And we're going to kind of discuss all that today. What does it all come down to? Again, the size of the atom and the distance from the electrons to the nucleus, and then in general, what's going on with that nuclear charge. Those three things kind of coupled all together, and it depends when you use which ones. So, again, you can just talk with your group. You can write on the board. I am going to suggest you writing on the board maybe as a group, and I'll give you a big hint, it's all about where the electrons are located somehow, okay? So you might be writing electron configurations, you might be looking at energy levels, what, okay? So we're going to take about 2 minutes each time, and then we're going to discuss it and write it down. So in the beginning, you're not going to present, so you can kind of write it out and talk about your notes if you'd like. Why is N more difficult to remove an electron than O? Now, that might be in the old notes, but I want to make sure all these situations come up all the time on AP exams. So this will come up somehow on Friday, many of these, okay? So work it out. If you already wrote it down on the previous notes, that's okay, but then talk about it to make sure that you're on the same page. If you need to draw it out, draw it out. Does anybody need paper towels? Luke, do you need a paper towel? We're only doing about 2 minutes per one, but these are really vital for us. If you haven't gotten to this point, you should at least have these, or these in your mind.
Like that's, this is like a so yeah.
Sounds like we're kind of slowing down a little. Please note, though, check it out. I didn't make you know that N was more difficult than O, okay? That's how the test questions go. Hey, it's more difficult to remove an electron from N than O. Account for that, or explain that in terms of atomic structure or electrons, or however it would be worded. Okay? So anybody want to take a stab? Rory.
O has one more electron, and it wants to be all the same, like all the same spins or whatever, so it takes it out. And then, well, that's what Jeffrey said.
You said the word want.
Oh,
oh my gosh, I'm having like a heart attack, I think.
I don't know.
Can't say want, right?
Yeah, I can't.
Because they don't want anything.
There's natural repulsion when they put in another.
Is that what Rory said? Are you guys just mimicking what each other said?
This is what I said. I said O would be, wait.
All right, so we're there. If you want to write these down, so on the back, I have it already written in a nice clean fashion. If you'd like, I already wrote which one was the stronger one. Thank you guys for volunteering. Again, it's not your job to know. For the most part, there's not many situations where it's like you got to come up from scratch. So you have to take the idea like, okay, this is more energy to or less energy to remove. I put this on the bottom versus this one. As Jeffrey had finished at the ending, there's a natural repulsion when electrons are paired up, so this one electron would be easier to remove due to that natural repulsion. Now you can continue to get further and further into that and say, well, they're still the same distance from the nucleus and all that. What is the one thing you cannot bring up which would be contradictory to your situation in this problem? Nuclear charge. Is O not greater in nuclear charge, which would be able to hold an electron stronger? But the data says it's not. So if you bring up anything about nuclear charge, you're going to probably get dinged, because that is not what, like, you're saying now it's more difficult to remove. No matter, and if you don't say that, then you're saying some incorrect statement about nuclear charge. Okay, so nuclear charge is I only bring that up when I'm talking about holding something stronger, holding something tighter. Okay, so I don't have anything else that's going to pop up. I'm just verbally saying these, and we kind of said this one the other day, but this one is, and pictures say 1,000 words, but without any words, it doesn't say enough. So do not just write those and write like bam, like there, thank you. Like you need to have some arrows and explain it, but this is great. You can draw these out, but you need to have some sort of a description. And just to finish this up, you can't hand this in, put an arrow and go, paired electrons. And then that's it. It's like, well, Mr. Essie, you know. It's like, I know, but do you? Like, prove it to me, please. Okay? So, natural repulsion. It must have a natural repulsion with just that one pair of electrons. Okay? So, here we go. Next situation. Again, about 2 minutes only. And I know these are on your notes, but we have some that are not. We have some that are not. So if you want to look these up or just discuss it with each other, but please be discussing it with each other. This isn't like I'm by myself, I'm a lone wolf. BE versus B. What am I saying? BE is more difficult to remove an electron than B. BE is more difficult than B. Got about 2 minutes. Again, you can write as much as you want. I'm not looking at these boards yet. It's more for your scratch work, if you'd like. You don't have to. Which one?
It's a marker sheet.
It's different colors. What'd you say? I am very cruel, I know. I'm glad the act is showing that. Got about a minute left. What has 4 lines? Oh, I see. Can do be talking. Writing's great, but it's not that big of a deal right now. It's more about just understanding the differences. We'll write it down on our sheet. If you have not at least thought about this, you should think about this. That's BE, that's B. Obviously, there's more to the situation than just that. There's nuclear charge, maybe. There's energy levels, maybe. There's distance, maybe. But at least I can talk about this in these terms.
Oh, that makes
All right, a different group. I mean, we're kind of finalizing ideas, but I'd like to hear it from groups and how they are saying this. Why is it more difficult to remove it from BE than from B, or vice versa? Why is it easier to remove an electron from B than BE? You can take either angle. So, Christian.
It's easier to
electron farther from the nucleus, which is easier to pull away.
Okay, I would add just one thing. Because of that electrons, it's in a new sublevel, which would be further from the nucleus. And there's additional shielding effect from an additional sublevel below it. So, and you could get really descriptive. B has only one s between itself and the nucleus, while BE has a 1s and a 2s